This is what we have been working our way toward with logarithms, and it's solving application problems. Some of these formulas should look familiar to you. We've got a compound interest formula and a continuously compounded formula. With both of those, the capital A is the final amount. The capital P, or the coefficient, is the principal, which is the initial amount that you start with. The R is the interest rate. T is time. And N in this formula means the number of times that interest was compounded per year. We also have exponential growth and exponential decay. Notice the difference. Growth adds on the rate, and decay subtracts the rate. In both of these, the y is the final amount, a is the initial amount, r is the interest rate, and t is time. Finally, we have a half-life formula. A is the initial amount, the base 1/2, the time that you're dealing with, and the assigned half-life time for the individual element. Let's look at some examples. Last year, you would have done an example like this. You deposit $1,500 in a bank, 6% annual interest. Find the balance after 5 years if the interest is compounded continuously. We'll use this formula. And you substitute in the information that's been given. Initial amount, interest rate written as a decimal, 5 years. And it's really just a plug and chug. I went ahead and multiplied the values in my exponent together. That way it's easier to correctly put into the calculator. 1,500 times base e to the 0.3 power would give us $2,024.79. Now that we know logarithms, we can start to solve for a value in the exponent, like here. You deposit $2,000, we've got 3.5% annual interest, compounded continuously. How long until our balance doubles? This is actually might be a more useful application for us. We're using the same formula, but once we plug in our values, 2,000 initial, doubled would be 4,000. Interest rate as a decimal, we're solving for time. You have to know logarithms for that. Let's solve. The first thing we're always going to do is divide by the coefficient. 4,000 divided by 2,000 is 2. Not a coincidence that we are doubling the balance. And we have a 2 here. Next, we're going to take natural log of both sides, since we have a base e. Here's an inverse property. And to solve for time, we divide both sides by 0.035. It'll take almost 20 years for our money to double at this particular interest rate. Example 3. You buy a new car. The value decreases or depreciates. We're talking about exponential growth. So let's plug in our values. Initial amount, rate, percentage rate, written as a decimal. Final value of $8,000. How much time? First step, divide by the coefficient. Now you'll get a decimal, which would be okay. I'm going to wait until the very end for my rounding, which is why I just have a simplified fraction. 8,000 divided by 22,000 would reduce to this fraction. I would take the logarithm of both sides. That allows for us to use the log property that this exponent can be written as a multiple, a multiplier. And then I can divide both sides by log 0.875. Be careful putting this into the calculator. You need to put, pay attention to parentheses and things like that. But we would yield 7.58 years. It will take that long before the car has lost a considerable amount of value. From $22,000 to $8,000 only takes 7.5 years. One more example. We've inherited some land. It was purchased for $30,000 in 1960. The value increases 5% each year. In what year is the land worth $300,000? We're working with exponential growth. Plug in the values: final amount, initial amount, rate, solving for time. Divide by 30,000 and we get 10. I also went ahead and added 1 plus 0.05. Now we'll take the log of both sides. Coincidentally, this does not always happen, but coincidentally, the log of 10 is 1 because log base 10 of 10. I'm just going to leave it as log 10 because that we're not always able to simplify there. Now that we have a logarithm, we can use a property of logarithms, bringing the exponent down as a coefficient, and we can divide both sides. It will take 47.2 years for the land to become worth $300,000. If it was purchased in 1960, 47 years later would be 2007. Have fun doing some of your own examples with practice.